Welcome to DRM1413 Manufacturing Technology, Chapter 4 on Rolling, prepared by Associate Professor T.S. Dr. Siti Rabiatul Aisha Binti Idris. This video will explore metal rolling technology, focusing on the process, physics, and equipment involved in this essential engineering technique. The content covered includes an introduction to metal forming and rolling, process analysis, common defects, and an overview of rolling mills. Metal forming is broadly categorized into bulk deformation and sheet metalworking. Rolling falls under bulk deformation, alongside processes like forging and extrusion. Rolling is a manufacturing process where a metal piece is reduced in thickness, changes its cross-sectional area, or is shaped via compressive force from a set of rolls. It requires massive, expensive machinery, suitable only for high-volume, large-quantity production. We differentiate between hot rolling and cold rolling. Hot rolling is performed near the melting point for massive bulk deformation. Cold rolling is done at room temperature for precision, finish, and superior dimensional accuracy. The industrial workflow begins with casting and soaking a steel ingot. This is followed by primary rolling into base shapes like blooms or slabs, and finally, secondary rolling to produce finished products like structural shapes, plates, and bars. Rolling processes are categorized into flat rolling, which reduces thickness, shape rolling, which creates complex shapes, ring rolling, which expands the diameter of a heated ring, and thread rolling, a cold forming process for creating threads on bolts. In the pinch point analysis, we look at initial and final thickness, draft, absolute thickness reduction, and reduction ratio. Volume is conserved, meaning entry volume equals exit volume. The neutral point is where the metal speed matches the roll speed, resulting in no slip. Metal enters slower than the rolls and exits faster. Forward slip measures the fractional amount of slipping at the exit. Material deformation is analyzed using true strain, based on the change in thickness, and average flow stress, which is the stress required to keep the metal flowing. Key material properties are the strength coefficient and strain hardening exponent. The governing equations cover maximum draft, which is limited by friction. We also calculate roll force, roll torque, and the mill power required to drive the rolls. Our first engineering application is determining the minimum number of passes and the draft for each pass in a multi-pass reduction cold rolling operation. To solve the problem, we first find the maximum draft, which is 7.875 millimeters. The total reduction requires 3.17 passes, meaning we need 4 passes, resulting in a draft of 6.25 millimeters per pass. The second engineering application involves calculating the roll force, roll torque, and power required for a single-pass rolling operation with given material and operational parameters. The solution involves calculating the contact length, true strain, and flow stress. Using these, we determine a roll force of 1.34 meganewtons, a torque of 14.99 kilonewton meters, and a required power of 37.65 kilowatts. The physics problem shows that force is directly proportional to contact length and roll radius. Large rolls require massive force. The engineering solution is to reduce the roll diameter to lower the required force. Structurally, small rolls bend under pressure, causing roll flattening. To utilize small rolls, engineers invented the 4-high and cluster mills, using massive backing rolls for rigid support. Rolling mill configurations include the 2-high mill, the basic configuration. The 3-high mill allows the work to pass back and forth. The 4-high mill solves the roll deflection problem. Cluster and tandem mills use complex backing networks for ultra-thin rolling or continuous reduction. Common material defects include wavy edges caused by structural buckling, edge and center cracks due to poor material ductility, and alligators caused by non-uniform bulk deformation or pre-existing metallurgical defects. For self-assessment, consider defining the rolling process, describing methods to reduce roll flattening, and explaining the concept of draft in a rolling operation. Also, identify ways to reduce force in flat rolling and other roll-based processes, and the limitations of small diameter rolls.